Hello everybody, welcome to another mini lecture in algebraic geometry. In this one we are going to talk about stalks, and we are going to bring in some perspective from commutative algebra. Namely, we are going to see that we can view stalks as local rings. So in other words, in case you haven't before, you will finally see now why local rings in commutative algebra were called local rings in the first place, because if you have introduced them in your commutative algebra course by saying that a local ring is by definition a commutative ring such that it has a unique maximal ideal, you do not necessarily know why this should be called local, and this is what we are going to see now. So let A be a point in a fine variety X, and let's look at a set S in the coordinate ring AX, which such that the elements of F are of S are the elements that do not vanish at this point A. This is of course closed under multiplication, and then we can look at the stalk of X at A, and we can localize the coordinate ring at this set S. And then there is, and this is what this is the topic for this mini lecture, then there is an isomorphism. So we show there is an isomorphism S inverse A X with a stalk of X and A. And remember, the stalk is made up of equivalence classes of regular functions, and two regular functions get mapped to the same equivalence class. Here, if you can find a small neighborhood of A such that they agree on this small neighborhood. And this is supposed to be an isomorphism of K algebras. So, proof. Well, I'm going to give a bit of a sketch of a proof and leave some details for you to work out. But I will show you, of course, show you the main points. First of all, let's have a map from the localization to the stalk. The elements of the localization are formal fractions of the form some polynomial g divided by some power of a polynomial f, where f is from this set S. And of course the regular functions are by definition such that locally you can express them as quotients of polynomials. So every regular function on a neighborhood of A has this form, where also f doesn't vanish. And yeah, to be correct, we need to look at the equivalence class, because we not only look at regular functions, but we project down to the stalk level. And then there is an obvious map, and it's also obvious that this is surjective. So for every for every equivalence class. That is, for instance, this one here, so that has as a representative gx divided by fx to the n. We just map this formal fraction to this, and this is by construction seen to be surjective, and of course also a K-algebra homomorphism. So this is remember, a K-algebra homomorphism simply means that this is an a homomorphism of rings, which is also a linear map, a vector space map, which is obviously true here for this map. So to show that this map, let's give it a name, let's call it phi. To show that phi is indeed an isomorphism, basically we need to do two things. We need to show that this is injective, and since we are dealing with equivalence classes, we also need to check that this is well defined. So maybe let's do well defined first. So phi well defined. Let's abbreviate it like this. So phi well defined. This means that if we look at two representatives of the same equivalence class over here and map to the stalk using this map phi, we have to make sure that they get mapped to the same element in the stalk. So let's see, if they are in the same equivalence class in the localization, this means that, well, let me write it down. So if g1x divided by fnx is equal to g2x fmx, this means, by definition of equality here in the localization, this means there is some h in S such that hx times g1x let's call this f1 f2x minus g2 f1 and x is equal to 0, right? You remember this means what it means. This is what it means that we have equality in the localization. And now let's look at the non-vanishing set of this polynomial, which we denote by, I mean the distinguished open subset for this. Yeah, H doesn't vanish on the distinguished open subset containing A, of course, and this means on this distinguished open subset, this is unequal to 0. So if this expression is 0, we have that this is 0. So we have that indeed G1. Well, it's obvious. I think I don't need to write it down. We have that these two need to be really the same, and thus this is well defined. So by injective, our strategy for showing injectivity will be the usual one, namely we're going to assume that an element over here gets mapped to 0 in the stalk, and then we need to show that this element is already 0. So in other words, we need to show that only the 0 gets mapped to the 0, so that the map is indeed injective. So let's look at an arbitrary element in the localization. Right. Then this gets mapped to this element in the stalk. And now if we want to say that this is 0, then this is the same as this element of the stalk. And what this means, of course, is that there is a small neighborhood of A such that this regular function and this regular function agree on this small neighborhood. But inside every neighborhood is a distinguished open subset, since these form a basis of the Zariski topology. So, so let's look at such a distinguished open subset. So let me write this. Consider dH. So this is now our distinguished open subset. And on this distinguished open subset we now have gx times 1, which is of course gx minus fx to the n times 0, which is of course 0, times hx. This h here is equal to 0, but this can't be 0 because we are, after all, on the distinguished open subset where h doesn't vanish. So this has to be 0, and thus we have this which of course looks the same as this one, but this is now true on all of x, and this says nothing but the equivalence class of this regular of this formal fraction is the same as this one. So assuming that an element gets mapped to 0, we have concluded that it is in the same equivalence class. It is a representative of the 0 element, and thus we have shown injectivity. And well, this concludes the proof. We have shown surjectivity. We have, well, I've told you it is an K-algebra homomorphism, and we have checked that it's well defined and that it is injective, and thus we are finished. Thank you for watching. See you next time.